Hello, my name is Se Chao, and today we will be working with vectors. Um, so we're going to start off by saying what is a vector, right? And then we're going to represent a vector graphically and mathematically. And then after that, we're going to see how to work with a vector. So we have the graphical and the mathematical way to work with a vector, right? And finally, we're going to take a look at some examples and uses of vectors. So let's get started. So what is a vector? A vector in mathematics, physics, engineering, it's a Euclidean vector is a geometric object that has a magnitude and direction. A magnitude is just the length of something. So what does that mean, right? A geometric object. Well, we got some geometric objects like triangles, squares, rectangles, etc. So what's the difference? So the difference is a vector has properties that has magnitude, direction. These don't have directions, right? They have lengths, but they don't have a direction. So let's take a look more into that. So what's the point, right? So what's the point of a vector? So here we draw a vector represented graphically with an arrow and points on the graph, right? So here we see that x equals 3, and y equals 4, right? Y-axis 4. So this arrow starts from the origin and it goes directed up towards 3, 4, xy, right? And we denote that with the symbol capital A. Could be lowercase a, but this isn't bold. So, and we'll talk about that. So as we said, a vector has magnitude and direction. So what is the magnitude and the direction of this guy? So let's go ahead and find that out, right? Because the magnitude is just the length. So that's pretty simple, right? We can use Pythagorean theorem to find that. So a squared plus b squared equals c squared, right? So here we'll say a equals 3, right? So 3 squared plus 4 squared equals, that would be something like 16 plus 9 is 25, right? And then to find c, we'll call this part c, which is the length. That will be the square root of 25, which is the square root of c, right? C squared, which is equals c equals 5, right? So the length we found, and it equals 5, right? It's just Pythagorean theorem. This side and this side square those sides will give you 5, square root of that. And now you want to find the direction, right? So that's also pretty simple. Here we're gonna say data. What is data? What is data? What is data? So from your trig is something like tan of data equals y over x, right? And then we take the inverse of that. Data equals tan minus 1 of y would be 4, right? 4 over 3, and that would give us something like let's take out our calculator. So gradients. So let's go ahead and put that in here. Tan of 4 over 3, and then inverse of that goes 0.0130 in gradients, right? So we have the angle go 0.013 gradients. So that's really tiny, right? Because we know this goes from 360 from the x-axis back is 360 degrees. So that's looks like a tenth, a little more than a tenth of a degree, right? No, 100th of a degree. Sorry about that. So so here we see that this arrow has properties. It has a length, which is 5, and it has a direction, right? It's given here. And so we're just going a little bit more about this vector. We're going to say we can denote it, symbolize it with here the capital letter A, or any capital letter, lowercase letter, as long as you boldin it. This is boldin. Or instead of bolding it, you can just say like something like A with a little hat on top, right? Or B with a little hat on top. That also tells us that we're working with a vector, right? So here you see it's boldin, but we could also write it something like that. A equals 3x plus 4y. So here, let's take a look at this x and y. So this is not the variable x, y. These are called bases, right? And these are called components of the bases, right? Components. This 4 and this 3, right? Because it characterizes or tells us where this vector is going, right? Where is it going? It's going here, 3 and 4. So these are called bases. And you will see maybe somewhere in linear algebra what these means. What these things say is that it just spreads, opens up a dimension for you to work in, basically something like that. Okay, but we'll talk about that later. So let's go on to the next slide. So what is a vector? We can represent it with components, right? 3, 4, and even with components. Instead of drawing it out, if we're just given this A equals 3x plus 4y, remember there's little hats on top of that, and those are not variables. Whoops, there you go. Sorry, this hats are pretty big, but you get the point. We can just pick them out, right? What is the magnitude? Well, it's going to be Pythagorean theorem, 3 square plus 4 square. Square root of that will give us the length. And the direction, we just take a look at this, and we don't have to draw it out, and we can find the direction by looking at these numbers. And that's the advantage of working with vector notation or with components, right? And just another way of representing a vector. So let's keep going, see what's next. So how do we work with vectors, right? Well, let's backtrack a little bit. Why do we work with vectors? With numbers, we can add, subtract, multiply, divide, and these things are used like for practical purpose, like money, or for geometry, we work with length. We can also multiply and add and subtract length, right? And these things give us things like distance, area, and volume. But with vectors, what can we do with vectors, right? And why do we work with vectors? Well, for example, let's take a look at gravity. Let's see if I'm still recording. Yes, I'm still recording. So, given a mass on a lever, right? So let's say this is some lever, and you got somebody sitting here, a stone, right? And it has a certain weight, right? So let's say this one is 1 kilogram. Now, how would you represent that weight of this stone on this lever mathematically, right? Or even symbolically, right? Well, we can say something like, oh, well, this we say from gravity is going to want to push it down, right? So here we draw an arrow, right? Look at that. That looks like a vector, right? And then we say, oh, okay, so it has a certain weight, right? We can say here it's 1 kilogram times gravity, right? Because gravity, remember, it's just a number. Okay, so then this, as you can see, vectors, this arrow here already has two things about it, right? It has a length, right? Which we can call the force down, going a little, which is represented by its mass and gravity. So that's we can say that's the magnitude, right? And then what about the direction, right? The direction, we say it points down, right? Down. So here we can say we can use vectors to represent something like a mass on a lever, right? So this is physical things and something that's pretty useful. Now, if we want to go ahead and add and subtract and multiply a vector by scalars, now what does that mean, right? What does that mean? Well, let's say we have a lever again, right? So we have a lever. This this looks like springboard, but this one is a real lever. Take a look. Right? So here's the fulcrum, and we have a bigger mass here. So we're going to represent that but with an arrow, right? A vector. So this one's going to be bigger, and this one's going to be smaller. It's be higher up, and this is going to be a smaller vector. So again, we can see like even with vectors, we can represent things, the difference of things, by drawing it to make it bigger or to make it smaller, just like on the graph, right? So now in physics, we want to balance this, right? We want to see where do we put this fulcrum to make it balance, right? Even though this is bigger, this is smaller, it would have to be somewhere, and this is the middle, somewhere over here somewhere, right? To make it balance. And to do that, you would have to use physics to add and do some physics basically to add these vectors together to see where would you put this fulcrum. So there is a point for using adding and subtracting and multiplying with vectors. But let's go on. So here we're going to say, let's go ahead and add and subtract and multiply a vector, right? Oops, did I miss something? Oh yeah, let's start here. So here we have two vectors, A and B, and they have components, right? 3, 4, 7, 4. So x and y's, right? So here's 3, here's 7. And they're both on y equals 4, right? So how do we add this, right? Graphically, to add them graphically, all we do is, whoops, we take this one, the second one, and we put it on the head of the first one. Therefore, we call it a tail to head method or something like that, right? So we take this and we put it on the top of the head of the first one, and then we get a resulting vector starting from the origin all the way to the end of the second one, right? And that will give us the sum of the vector, right? So here we can see that we can certainly add two vectors together. Now, would it be the case where here we say this is a plus b, right? A plus b equals c. Now, would it be the case where b plus a equals c? Because, for example, in regular numbers, right, we can say 1 plus 3 equals 4, and also 3 plus 1 equals 4, right? So that's okay, right? But would this be okay, right? And so that will take us to the what is called a parallelogram description, and that would show that this is also indeed the case where b plus a does equal c, right? But here, let's take a look at adding it by its component. So c, we can say here, right? C equals 8, 10, right? So c has points that is 8 and 10, right? Now, can we get